Hi. In this video, we're going to go through a few worked problems focusing on the ideas of addition and scalar multiplication of vectors and matrices. The first problems we're going to work through are a couple of problems put up here. I recommend that you pause your video at this point, read through the questions, and then when you've done your own work, then resume to see the solved solution. Okay. So we want to compute the operation involving these two vectors, u and v. The first one, 2 times u plus v. Here, we're combining a scalar multiplication and an addition operation. Remember, scalar multiplication involves simply multiplying every element in the vector by the same scalar. So 2 times u, 2 times the vector 1, 0, 2, is simply 2 times 1, 2 times 0, 2 times 4, or the vector 2, 0, 4. We then want to add that product 2u to v. And we do this with element by element addition. That is, we add together the corresponding elements of the two vectors. 2 plus 1 is 3. 0 plus -1 is -1, and 4 plus -1 is 3 for our final answer. The precedence that we take multiplication before we do addition follows the same rules as with scalar arithmetic. Our second example is again a combination of scalar multiplication and an addition, noting that subtraction of a vector is the same as adding a negative multiple of that vector. Again, we take the multiple first, 2 times v, where v is 2, -1, -1. Multiply all of those terms, 2, -2, -2. We then subtract that vector from the first, from u, and do that element by element correspondence. 1 minus 2 is -1, 0 minus -2, so 0 plus 2 is 2, 2 minus -2 is 4 for our final answer. Quite straightforward. Now, let's do the same sort of thing with a few matrices to get a feel for how we do the same types of operations, but on matrices. Again, I recommend that you pause the video at this point, work through these two problems, and when you're ready to check your work, then resume to see the solved example. All right. The first example we have, 2a plus 3b, is an addition of two scalar multiples. Again, we take the scalar multiples first, then add the results. 2 times a, where a is the 2 by 2 matrix, 1, 0, 1, 2. We multiply the scalar by all of these elements, every element multiplied by the same scalar. So 2 times 1 is 2, 2 times 0 is 0, 2 times 1 is 2, and 2 times 2 is 4. Doing the same idea with the second scalar multiple, 3 times b, where b is a 2 by 2 matrix, 0, -2, 1, 1. All of these elements multiplied by 3. 0 times 3 gives 0. -2 times 3 gives -6. 1 times 3 gives 3, and this is also a 1, so 1 times 3 is 3. Once we've taken the scalar multiples, add the corresponding entries. Matrix addition simply adds corresponding entries. 2 plus 0 is 2. 0 minus or plus -6 is -6. 2 plus 3 is 5. And 4 plus 3 is 7 for our final answer. Both the matrices we were working with are 2 by 2 matrices. The answer is a 2 by 2 matrix. Scalar multiplication and and matrix addition always require matrices of the same size, and the result is a matrix of the same size. Now a slightly more involved example where we have a scalar multiple of a difference of matrices, then an addition of an additional matrix. Again, the same rules of precedence in operations apply as you're used to for standard arithmetic. So the first thing we need to do is to evaluate this difference inside the parentheses. Right? This difference is found by subtracting the corresponding elements. So 1 minus 0 is 1. 0 minus -2 is 2. 1 minus 1 is 0. And 2 minus 1 is 1. So this piece here is the result of that first difference. Then we apply the scalar multiple to that difference. 2 times this matrix here. We apply the same scalar multiple to every element. 2 times 1 is 2. 2 times 2 is 4. 2 times 0 is 0. 2 times 2 is 2. Once we have this, then we can add in the matrix C, and again, add corresponding entries. 2 plus 2 is 4. 4 plus 3 is 7. 0 minus 1 is -1. And 2 plus -2 is 0. Again, fairly straightforward. Just remember scalar multiplication. You multiply every element by the same scalar. Vector addition or subtraction, you add or subtract the corresponding elements in the matrix or the vector. All right. The next problems I want to sort of work on look at the idea of linear combinations. We're given two vectors, u and v. The same two that we worked with in the earlier problem. And we would like to find linear combinations of u and v that equal the w that we're given. And we're given 3 different possible values of w. Again, please pause the video. Do your best to find these linear combinations on your own. And then when you're ready, return and watch as we work through each of them. All right. So first of all, let's just recap what we mean by a linear combination. Right? A linear combination is a sum of scalar multiples. So a linear combination of u and v is some constant a times u plus some constant b times v. And what we're trying to do in this problem is find a and b such that w equals a times u plus b times v for a given w. It's possible to actually just solve these sort of from scratch for each new w, but it actually, because in every case we're going to have w equals au plus bv and then trying to find a and b, it actually can help just to think about that little piece first. Right? What does AU plus BV look like? And one thing that is actually very important about sort of this particular sort of combination with U as it is structured, because U has a 0 in the middle, the second element, that second element always will be 0. Doesn't matter what A is. A times 0 will always be 0. So the middle element of A times U will always be 0. That means the middle term in W, in a linear combination, is only going to come from BV. Can't have any contribution from U because U has a 0 there. Right? We can summarize this and actually add a little bit more information by just asking what is the sum AU plus BV using these symbolic constants. We don't know what they are yet, but we know they have to be something. So we use A and B as placeholders and evaluate this sum. A times 1, 0, 2 plus B times 1, negative 1, negative 1. We apply the scalar multiples first, applying the same scalar multiple to each element. 1 times A is A, 0 times A is 0, 2 times A is 2A. Same for the second product. Apply B times 1 is B, B times negative 1 is negative B, and B times negative 1 is B. Adding these two vectors together, adding the corresponding elements, A plus B, 0 minus B, or negative B, and 2A minus B. And this now is a general form for what AU plus BV looks like, written as a vector, but with A's and B's in place of the numbers. Once we have this, it's easy for us to now take a look at each W. Right? If W is 2, negative 1, 1, what we'd like is A plus B to equals 2, negative B to equal negative 1, and 2A minus B to equal 1. Because of the simplicity of the second term, that it's just negative B, we can directly from this W read off that if W is the second term, second element of W is negative 1, that has to be negative B, so B has to be 1. Right? If B has to be 1, then how can we get A plus B equals 2? We can get that by A equals 1. We should always double check. We don't just stop here and say, I have an A and a B, I'm done. Let's look at the third term. How can we get 2A minus B equals 1 if B equals 1? Well, if B equals 1, then 2A has to be 2, which means A has to be 1. Again, we get A equals 1. We got a consistent answer whether we looked at the first term or the third term. Right? So, plugging in A equals 1 and B equals 1, we really see that we have W equals U plus V, or 2, negative 1, 1 is 1, 0, 2, plus 1, negative 1, negative 1, and a quick double check of the this addition shows that this is, of course, correct. 1 plus 1 is 2, 0 minus 1 is 1, 2 minus 1 is 1. All right, let's move on to our next choice of W. Different choice of W, but the same general expression for a linear combination of U and V. We can take a very similar approach. Look at the middle term. The second term of W is negative 3, therefore B has to be negative 3. If B equals, not be negative, positive 3. If B equals 3, and a plus b has to equal 2, then a must equal -1. Right? Similarly, if b equals 3 and 2a minus b equals -5, then 2a has to equal -2, and a has to equal -1. So, again, consistent results. A equals -1, b equals -3. The linear combination we have is that -1 times u, 1, 0, 2, plus 3 times v, 1, -1, -1, should equal our w. And double checking that that's true, -1 plus 3 is 2, 0 minus 3 is -3, -2 minus 3 is -5. It all works out. So one more example. Let's do the last case. And here we're going to run into something a little bit different, a little bit of a problem. We start the same way. We take a look at the second term of w. It's -2. Therefore, b has to be 2. If b is 2 and a plus b is 4, then a has to be 2. But in this case, if we look at the third term, 2a minus b has to be 0. If b is 2, then 2a has to be 2, and a has to be 1. We get different answers for a, whether we look at the first term or the third term. This inconsistency tells us that there is no way to write w as a linear combination of u and v. This example is important for two different but related reasons. First of all, it highlights the fact that you can't always write an arbitrary vector as a linear combination of other vectors. Right? This is a property that is going to be incredibly important, is going to give rise to ideas like vector spaces and subspaces, and is really central to a lot of linear algebra. Not every vector can be written as a linear combination of an arbitrary group of other vectors. There are some sets of vectors where you can write any vector as a linear combination, but others they can't. Secondly, more from an operational point of view, we learn how we can tell when a linear combination can't exist. When we get an inconsistency in our solution like this, this tells us that the problem we're trying to solve doesn't have a solution. This is also going to be something that we use frequently. When we reach an inconsistent solution, we get two different answers for the same variable. Depending on how we approach the problem, that is generally an indication, as long as you didn't make any errors, that the system does not have a solution. Okay. That's it for the examples, the worked examples from this section. There's some more practice available for this on the homework. Thank you and goodbye.